Hello, students. This is Professor Scott Norman from Pittsburgh State University in the Department of Automotive Technology, and this is our second installment of the series of how does AC systems work on mobile vehicles. The first video was part one on capillary TXV systems, and so if you haven't already seen that one, I would recommend watching that one first because I go through a whole bunch of basics on that first video that I won't get on the second video. So this one is then going to be highlighting H-valve systems. And so when we look at a H-valve, this is still a TXV system, a thermal expansion valve systems. And, they started to go to an H-valve instead of a capillary tube because everything is built into this, what they call an H-valve, that if you kind of look at the lines going in, I got, here's my liquid line. And liquid line going in, liquid line going out, and then you have your suction line going in, your suction line going out, and it kind of looks like an H. That's why they call that an H valve. But this H valve could be, typically it's on the bulkhead. Typically you can see it. Sometimes it's facing straight up and down like this. Sometimes it's facing sideways, but typically you only see half of this. So you see the side that the tube, the suction line is going to the compressor and the liquid line is going to the receiver dryer. You do not see the other half because that's like under the dash. So you only see half this valve from the bulkhead. But again, this power dome is the key because sometimes this block, this aluminum block, is just a connection between the suction line and the liquid line to the two lines at the evaporator. And so the way to tell the difference between if it's just an attachment block versus the H valve is, again, you're going to look at this power dome. And if you see that power dome, yep, that's my H valve. Again, Chrysler Corporation started to use them lots. And really, if you take a look at most domestic manufacturers, they're using a TXV system. Really, everyone's using pretty much a TXV system. Now it's hard to find a new orifice tube system on a, say, 2020, 2021, 2022 vehicle. But a lot of them are going to the H valve just because it's simpler on that. So as we get started, as a reminder, you should be able to identify your four main components of the system. And I call those the four main components because, you have two pieces that are the heat exchangers, and you have two pieces that are the pressure dividers, I'll call them. And so that's why I say there's four main pieces in every AC system, and then you have this fifth one right there, depending upon what device is controlling the amount of refrigerant going through the evaporator. And so this is, I guess, a time to pause and make sure you know what those are. You kind of like guess at them yourself, and I'm going to give you the answers now. So hopefully you figured out that our compressor is over here. So that's, that's the heart of the system. And then we got the condenser where the refrigerant's going, out of the compressor to the condenser. And then we have the receiver dryer. And again, the receiver dryer on most newer vehicles is attached right to the condenser itself. Excuse me. And so, it's you don't see it. It's hard to see. And so coming out of the receiver dryer, this liquid line goes all the way from, in front of the radiator, all the way. Typically, it's on the passenger side of the engine compartment, but sometimes it's on the driver, and then it goes all the way to the H valve. And so that's a pretty big, long liquid line. And then if you look in the engine compartment, then you'll see this line right here coming out of the TXV, which is your suction line that is going back to the compressor. So you have three main lines. You have your suction line that you can see, you have your discharge line that you can see, and then you have your liquid line that you can see. I'll play the animation so you can kind of see the refrigerant going through everything, but remembering that discharge line should be hot to the touch. The liquid line, where there's a liquid high pressure refrigerant in there, it should be warm to the touch. Then if you grab this suction line right there, that should be cold to the touch. So how this system works different from a capillary system is that everything is kind of built into the H valve itself. So you still have your power dome up here on top, and you have refrigerant on the very top of that power dome, and that refrigerant is going to depend upon what the pressure is of that refrigerant or the temperature. If the pressure is high, if the temperature is high in that power dome, then this pin inside here is going to push down, and as it pushes down, it's going to open up that valve and allow more refrigerant to go through. If the pressure on the top of this power dome is low, below 20 psi, well, there's not as much pressure pushing down on it, and this spring at the very bottom is calibrated, and there's typically a cap at the bottom of your H-valve that seals that. If I ever see that cap off, I'm very concerned. Somebody took that off and maybe tried to tweak a screw in here to try to change the pressure, which then changes the the way that the H-valves work. So yeah, don't mess with that screw. But anyway, if there's less pressure up here, then this spring is going to push up, and it's going to close the valve, kind of like what we see right here. And so it's all basically internal. The suction line right here, the pressure that is in the suction line coming out of the evaporator, if it goes up to, let's say, above 40 psi, well, 40 psi, temperature around 40, and so that high pressure, high temperature is going to be sensed by a sensing sleeve. The temperature is actually being transmitted through these pins up here, which is then going to warm up the refrigerant, and it's going to push down, and it's going to allow it to open up. If the pressure in the system, drops down below 20, well, there's, 20 psi, 20 degrees, we'll say, give or take a little bit. But there's not as much temperature, it's colder, and so that temperature doesn't warm up that power dome as much, and so there's less pressure up here, which is going to cause this guy to move up. So it works under the same principles of a capillary system, except everything is built inside. And so on a hot day, it's 100 degrees outside and you have a heavy heat load, you're going to want as much refrigerant as possible. So you'll see that your low side pressure goes from 20 to 25 to 30, 35 to 40. It starts going up higher and higher and higher. Well, we're gonna open up this power dome, and we're gonna allow as much refrigerant to go through it as possible, because the evaporator could handle it. There's so much heat load inside the car that all the refrigerant evaporates, it boils. And so I have a significant amount of superheat coming out of the evaporator being sensed by the H-valve, which is allowing it to open up. On a day like today here in Kansas, look at my computer, it's 13 degrees outside, so a nice snow day for us. On a cold day, and if your AC, eventually kicks on when your engine compartment gets warm, and maybe you need the defroster or something like that, and the AC kicks on, well, you're going to not have any heat load here. There's going to be hardly any heat, and so the liquid refrigerant's going to go into the evaporator. There's not enough heat load to evaporate the whole entire amount of refrigerant, and so it's going to get really cold. It's going to be evaporated in this line. It's going to be evaporated in the H block. It's going to get very cold in here, and then again, that cold is going to allow less pressure to come up on here, and it's going to push the valve up. And so it's going to restrict the system. And again, we're wanting to regulate the exact amount of refrigerant going through the evaporator at all times. So I am completely evaporating the refrigerant in the evaporator, not before it. If I see this line before the evaporator frosting up, meaning that there's probably boiling going on here, it could be that this H-valve is being restricted, that it can't move open. If I see the outlet of the line, I guess when I'm looking at it, you probably won't see that line on a realistic car. But let's say if this suction line right here, if I see that frosting up, I'm very concerned, because that means that there's still refrigerant boiling, getting super cold, and it could be that this is stuck open on a mild day, and you don't have enough heat load to boil all the refrigerant, and so you got this liquid going to the compressor, which is very, very bad. So when we talk about the different types of problems, I typically, will throw out different scenarios to my students. Hey, what if the compressor fails? What should you do in the system? And it depends on who you work for, it depends on the answer, because let's say that I have a compressor failure because maybe it's leaking. The case half right here maybe it's leaking, not a compressor failure internally, it's just that, hey, it started to leak, so I have to replace it. We're not really rebuilding compressors anymore at dealerships. And the car has, let's say 50,000 miles on it or whatever. Well, you're obviously going to replace your compressor, and you're always going to replace your receiver dryer because the receiver dryer is acting as a filter in the system. It also has the desiccant. So I'm definitely going to replace those two pieces right there. I am not going to replace my H-valve. And with working for Chrysler Corporation, we never, if someone put a compressor and a receiver dryer and an H-valve on a warranty repair, that was typically like a question. It's like, wonder why they replaced the H-valve and the compressor and the receiver dryer. Were they just guessing, doing like a shotgun approach? Or was the H-valve really bad, which caused the compressor failure? Which it could be, but if you're replacing your H-valve and the compressor, I would probably want some good write-up on why you did that. So let's give you a different scenario. Instead of there being a leak at the compressor, let's say that the compressor is physically locked up. It's locked up solid. Well, now I'm a little bit more concerned because it's like, well, why did that compressor lock up? Was it due because of the lack of oil? Was it because there was a malfunction in the H-valve causing the problem? Was there debris coming out of that compressor going through the condenser, maybe hanging out at the receiver dryer? Typically, let's say that some debris did come out, and I would know that because I would backflush my condenser, which, there is a controversial thing, but at least I'm going to try to backflush it, and I'm doing it for diagnostic reasons to see if I have any debris coming out. So I can't say for sure I'm going to clean that condenser out thoroughly, but I'm doing it to see if there's any debris in there. That's all. So I tend to do that. I'm always going to replace the compressor and the receiver dryer together. Those are a package piece. But it's that H-valve tends to be, I tend to only want to replace him if I think he caused my problem. And there's some ways you could test him fairly easy in the shop to make sure he's moving. Again, there's two scenarios on how this H-valve would cause this compressor to fail. Number one, it's stuck closed. It's kind of like what you see right here. And if it's stuck closed where you're getting very little refrigerant going through the system, that also means little oil, and I'm worried about starvation of oil of that compressor, which is then going to cause it to fail. The second scenario is that it's stuck open and there's too much refrigerant going through, and if that's the case, then you're going to get liquid refrigerant going to your compressor, which could also cause the compressor to fail. So, like if I buy a compressor at Napa, for an example, and again, I want to get their kit. Sometimes they'll come with the compressor and the receiver dryer and the H-valve, all as one assembly, all as one kit. And it's like, if I'm working on my car, I may not replace that H-valve until I put that compressor on, get it running, and then do some diagnostics and see if this thing is working or not on that. If the compressor is, if the H-valve is stuck closed like it is right here, I'm going to get a very low reading on my low side. So my low side, it could be in a vacuum if it's all the way plugged up and clogged and there's no refrigerant flow at all. But if it's restricted and not opening, I see maybe 10 psi, 15 psi, somewhere below 20. And then my high side, is 100 to 150. So it's indicating a problem. What I would do next is I would, so again, that's one scenario, is that my pressure readings would indicate if this was stuck closed. Another thing that I like to do is I like to run the AC system, and I turn the AC system off, and I watch the equalization pressure, how long it takes the low side and the high side to equalize. And you have to realize is that when I turn my car off, the H-valve wants to go into a closed position like this. And so equalization will take quite a long time. It may take, 10 minutes, 15 minutes, 20 minutes. And so if I don't see the pressures equalizing between my low side and my high side at all, after 30 minutes, there's no equalization. My low side reading is still reading, 10 psi. My high side reading is still reading over 100. I'm concerned that there's a restriction in the system on that. A couple other things I could do is I could spray a supercoat substance on this power dome, which I have lots of videos that are showing that. And I also have lots of other videos under lessons of TXV that is showing equalization rates. But anyway, if I spray a whole bunch of refrigerant on this, while the system's running, I should be able to get this power dome to, trick it to close. I put a super cold substance on that, like CO2. It's going to make it cold. There's going to be less pressure up here, and it's going to close. And so the other scenario would be is that I think it's stuck open. If it's stuck open all the time, I typically have my low side pressure is going to be a little bit higher than normal. Maybe it's at 40. Maybe it's at 35, but it's just not dropping down as low as it should. Car's not cooling right. I'll go ahead and I'll put some CO2 on there, and as I spray some CO2 on there, if my low side gauge drops to 15 or 10 or even down to 0 or even to a vacuum, I know at that point that this is capable of closing, and at that point, hey, it's working. So there's things I could do to test this besides just guessing to see if it's physically opening and closing on that. When I shut off my car and shut off my AC systems, typically the gauges will jump up a little bit. So maybe my low side pressure was 20 psi. I shut my car off, it jumped to 25, and then all of a sudden it started to really equalize slowly. So that kind of seeing that jump of pressure tells me that, okay, it was open. I shut my car off, the TXV closed, and now it's in the equalization process. So there are some things to do with that. But, for customer satisfaction, I could see a technician saying, hey, my compressor is failing. I can't test this very well, so I'm going to put an H-valve on, a compressor, and a receiver dryer because I want to make sure that my customer is satisfied. A lot of guys are now also, if they have something like the compressor locked up, they're going to put a condenser in with it, because they know realistically they can't backflush this condenser and clean it out. And so, and sometimes the receiver dryer is just part of the condenser. And so it comes as one package. You can't rebuild the receiver dryer. So now you have a compressor failure. You're replacing the compressor, the condenser, the receiver dryer, and the H-valve, which is obviously a big repair. Next thing I'm going to do is I want to click on this H-valve to kind of show you guys a little bit more as far as how it operates on there. And then so what I tell my students here, and let me see, this is probably going to, see how the H-valve is going up and down. So right now it's closed. And then as the power dome goes down, now it's open. So it's just going to go open, close, open, close, open, close. But what you have to realize is that if you have, and this is what I tell my students they have to know for their exam, is that when you have a high heat load condition, so that means, it's 100 degrees outside, it's 130 degrees inside your car, in the parking lot. So when you start your AC system, your suction pressure is going to be up high. Okay, so that means that the diaphragm is going to be pushed down, and that diaphragm is going to push down. It's going to operate that pin, which is going to push down, and it's going to open up. That's the key, is that's going to open up the valve because the evaporator could handle it. It's so hot inside your car that that you have a high heat load, that all the refrigerant inside the evaporator is going to evaporate because of the high heat load, and so it can handle it. So let's put as much refrigerant as we can in there. The other scenario, is that it's 13 degrees in Kansas here. You have a low heat load, so suction pressure is going to be down way low, typically below 20. So the diaphragm is going to be in the up state because you get this less transfer of heat to the power dome up here. The pin's going to move up and the valve is going to close. So on a mild day, on a low pressure, the valve closes. Goes up and down and up and down. This system that I have here has, here I'll show you the call outs, that way you can kind of just see the different names of the pieces of the H-valve internally. We have some narration that this guy's going to go through. We're going to listen to it because there's some mistakes that they say, which I think is kind of interesting, and then I'll explain that. So we're going to listen to what they say. I think it's going to pick it up on our audio. We'll see what happens here.
The H-valve regulates the flow of liquid into the evaporator so that when the refrigerant leaves the evaporator, it is completely vaporized. It's called an H-valve because it has a shape that resembles the letter H. The H-valve consists of a 4-port body, control power dome, pressurized diaphragm, temperature sensing sleeve, moving rider pin, ball and seat, and spring. refrigerant enters the H-valve on the lower port and is regulated through a variable orifice. After expansion, the refrigerant exits the second lower port and enters the evaporator. From the evaporator, the refrigerant re-enters the H-valve through the upper inlet valve port. The refrigerant passes over the temperature sensing sleeve, transferring heat to a small amount of refrigerant within the power dome. The refrigerant expands and contracts based on the temperature of the refrigerant passing through the H-valve. The action of the refrigerant in the sensing cavity modulates the flow of refrigerant into the evaporator. Movement of the diaphragm is also controlled by the compressor's suction pressure. The diaphragm responds to pressure increases in this area by increasing the flow of refrigerant into the evaporator. As the diaphragm expands, an attached rider pin is forced against the ball and seat. This increased force of the rider pin against the ball and seat compresses the spring. As the spring compresses, the ball and seat move, increasing the size of the expansion orifice, allowing more refrigerant to enter the evaporator. Cold or excess refrigerant lowers sleeve temperature, causing the diaphragm to contract, which forces the attached rider pin to move. The valve spring forces the ball against the rider pin. The greater spring effort pushes the ball into the seat, reducing the size of the expansion orifice. As the size of the orifice is reduced, the amount of refrigerant into the evaporator is restricted. Typically, H-valves use a notch on their orifice seat to prevent the ball from completely sealing against the seat and causing excessive high pressure in the event of an H-valve failure, overcharge, or extreme temperature conditions. The notch preventing the ball from completely sealing the valve also keeps oil circulating to the compressor at all times. With some systems, it's important to remember the orifice seat may be designed without a notch.
Okay, so I'm going to try to pause this here for a moment when the seat is closed. So there it's closed right there. Boom. Good. That's good. So what they're showing you here is that this little notch right here, and so some H valves have a notch and some vehicles do not have a notch, and it's easy to know which way it is because when I put CO2 on this power dome and I get this to close, if the lowest my low side pressure goes is, let's say 5 psi, it doesn't go into a vacuum, then I know that there's a notch there. If I put CO2 on this power dome and my low side drops down into a vacuum, 10, 15 inches of vacuum, and it is creating a vacuum because this is all the way closed, I know that there's no notch. Another thing I could tell by if there's a notch here or not is if I do an equalization test. That's when you're, again, turning off the AC system and you're watching the low pressure and the high pressure equalize. If it equalizes in, let's say, 5 to 10 minutes, well, there's probably a notch there allowing it to equalize a little bit faster. If it takes 20 minutes to equalize, longer than what I say normal, then chances are is that there's no notch. Now, one thing I thought was interesting is that this animation, this narration, said that this little notch is here to prevent high side pressure from going up high if there's a restriction here. And that is a false statement. If there's a restriction anywhere in here, high pressure will not be high, won't be high. And I'm very confident on that. And so the reason why I can tell you that is, number one, I go into my cars and I restrict this in my students quite often, put a restriction in here so they have to diagnose it. Also, if I put CO2 on this power dome and get this to close, I could simulate a restriction to see what it looks like on the gauges. And never once has it ever gone high. And let me explain why that happens. And so if there's a restriction, I'll play animation. So if there's a restriction right here in this in the H valve right there, I'm gonna let the refrigerant go through, and here we'll stop it. It won't let me to stop it. Oh, maybe I'll pause it. Let's try that. So here I'm gonna simulate a restriction here. Hold on. So it goes here, boom, and it pauses. Okay. So it's all the way closed right there. So if you take a look at it, what happens is that if the H valve is closed right there, and we create a vacuum in the low side section. So we create a low side. So we're pulling all the refrigerant out of the low side area, okay? And so that suction hose and the amount of volume, think about the size of a evaporator. It's not very big. Now take a look at the compressor. The compressor is going to take all that volume that was there and it's putting it in the condenser. Think about the condenser. How much bigger is the condenser versus the evaporator? And also look at where your storage device is. You have storage in that receiver dryer. So what ends up happening is that the amount of area that the refrigerant has to stay in on the high side is a lot bigger than on the low side. So if there's restriction there, so when I operate a system, let's say that my my low side's at 30, my high side's at 150, and I put a supercode substance of refrigerant, or let's say CO2 on here, and get this to physically do this, I'll see my low side drop into a vacuum if there's no notch in that seat, and I'll see my high side pressure, if it was 140, maybe it drops to 130, 140, but it drops a little bit, but it doesn't go high. And it's simply because there's a lot more volume on the high side than there is on the low side. That you suck all this refrigerant out and you can't pressurize anymore, and there's still space over here. And so make sure you guys realize that. And again, and you can watch my other videos I have on lessons on TXVs, to where if there's restriction in the TXV, it will not cause high side to go high. It causes high side to actually go low. And low side would be very, very low on that. I'll go ahead and I'll continue with that. Okay, we're at the 26-minute mark, so let's go ahead and let's sign off on this particular series of video. Hopefully you enjoyed it, and if you're looking for more automotive educational type videos, please subscribe to my Professor Pintang YouTube channel. Stay on the lookout for part 3, where we will cover some orifice tube systems. Thank you very much. You guys have a good day.